My name is Simon Shim. I'm one of the guest editor of the special issue on new generation memory. Today's interview is with Steve Swanson, who is associate professor at UC San Diego. My first question is, so how are these new memories going to change the system architecture overall?
Oh, well, thanks for having me on here, Simon. I think what we see as the big change that these memories are going to bring about is that it's going to really shift the way that we design both the hardware and the software in the systems that are going to incorporate these memories. So on the hardware side, as new technologies come along, we have to find new ways of connecting them to the system. So we're going to have more solid-state drives based on these devices attached via things like PCI Express and future versions of the SATA and SAS standards, perhaps. But the biggest changes that we've seen as we've gone through and built some of these prototype SSDs, and we've built prototypes using both DRAM, and we also built one of the early PCM-based solid-state drives, was that the biggest change comes in the software. And the reason for that is that over the last 40 years, we've been dealing with storage devices, namely disks, that are very, very slow compared to software. And as storage systems have evolved, we've added many layers of software complexity to those systems. We've added kind of abstraction layers in the kernel. We've added pretty heavyweight file systems that provide lots of very interesting and useful functionality, but we haven't had to pay too much attention to the performance of that software. So in the past, you could actually add software to your storage stack, and the performance of your overall storage system would go up because maybe you could schedule accesses to your disk more intelligently, or you could do something like on-the-fly compression that would improve bandwidth, and you could do encryption and all these other very nice features that we've come to depend on a lot of storage systems. Those are basically free in terms of latency and overheads. And now we've seen with these new technologies, first with flash and then with phase change memory and spin-torque MRAM and the memristor, and some of these other technologies that are coming down the line, is that the hardware latencies for storage are going to drop by many orders of magnitude. We're going to go from milliseconds down to nanoseconds in some cases. And that completely shifts the balance between where the costs are. Where software used to be free, now software is actually very expensive. And so if you look at the software stack for kind of the stock storage software stack in Linux, it's about 17 microseconds from the application level down to kind of the hardware interface. And so for a hard drive, that's basically free. That's 17 microseconds on top of 11 milliseconds. But for the prototype devices that we've built in our lab, that's 17 microseconds of software overhead on top of just maybe 4 or 5 microseconds of hardware cost. And so the balance has really shifted. And so what we've had to do is go through and really try to trim out as much of that extra software overhead as possible, and gone through a lot of effort to kind of refactor the system to get the software out of the way as much as possible. And that's had a pretty profound effect on what the resulting storage stack looks like. So in our system, you establish a connection with the storage device, and then the application talks directly to the storage device. It doesn't go through the operating system, so we're able to eliminate all of that overhead. But the challenge, of course, is that once you do that, once you get the operating system out of the way, in most cases, you need to still provide all of these other features, things like reliability and rich file system semantics and encryption and security features and all this other stuff. And so we've started the process of rethinking how to integrate all of those features into a much, much faster, much lighter weight software stack that sits on top of our storage device. And what we've done so far is really just kind of the beginning. So we've got a pretty good handle, I feel like, on the operating system. We have one approach that we think works pretty well. There are probably others. But that still leaves a bunch of applications that need to worry about this stuff as well. So databases, for instance, go through all this trouble of scheduling accesses and very carefully managing storage, and many of them take over many of the features of the file system, and those layers have all been optimized for disk, and so they probably have the same overheads that we saw in the operating system, and they're going to have to be kind of redefined and re-engineered as well. And so these new memories are really going to, kind of shake the bedrock of how we deal with storage and the memory hierarchy, and are going to cause us to rethink all of the code that's been optimized, for slower technologies, and that ends up, as we found, to be a really surprising number of different components in the system, and so the changes are going to be pretty far-reaching.
Okay, so my next question is, so what are the challenges remain for these new memories?
Sure. So I think there are several. Some of them I just touched on. So there's this question of how other layers of the software are going to adapt to these new memories running underneath them, and how we're going to have to rethink the design of that software and maybe re-engineer it pretty significantly. There's also questions about how they're going to be attached to the computing system, and those are going to need to sort of get sorted out both by academic researchers and folks in industry. So right now there's, you can buy PCIe attached solid-state drives based on flash. It looks like, in the next few years we're going to start seeing non-volatile main memory, putting phase change memory or spin-torque MRAM or the memristor on top of or attached to the DRAM bus of processors. And there's pros and cons for each of those approaches, and they're probably going to coexist, but figuring out kind of which of those architectures is best suited for different applications, which one makes the most sense in terms of cost, and how maybe in a system that has both, how those are going to interact with one another. And how do we balance the amount of non-volatile main memory versus the amount of conventional DRAM main memory versus the amount of high-speed storage sitting on PCIe, and then also, of course, how that integrates into the data center at large, right? So people build, we build small storage systems for laptops and so forth, but nowadays all big, interesting storage systems span many, many machines. And they bring with them a bunch of new challenges. We now have network delays we have to worry about, and it's kind of similar to what we saw with the software costs. As storage gets much faster, the relative cost of the network goes up dramatically. And there's a danger, if we don't figure out how to engineer these systems effectively, that the network latency is really going to end up being the limiter on our ability to exploit these very fast memories. Because if we have 15 microseconds of network latency to access our 5 microsecond or 100 nanosecond non-volatile memory, then that's going to be a real problem. And so looking at new approaches to building these distributed systems that require less communication, or optimize that communication in a different way, or somehow get that communication off the critical path. All of those are, I think, what's going to have to happen for these technologies to really have kind of their full potential realized. Otherwise, there's a danger that they'll end up confined a little bit more to a single node. I don't think that's going to happen. I've heard ideas from folks about how we could address this, and my lab is working on some ideas in that direction as well, but it's not at all clear how that is going to play out. So that's one area, sort of extending to the data center. The other question that we need to answer is, how are these memories, if we put that non-volatile memory onto the DRAM bus, how is it going to interact with the rest of the processor hierarchy and memory hierarchy? What kind of support do we need to add for strong consistency guarantees in the memory hierarchy? Right now there's no way to tell, if I update a piece of memory, that the update has actually been propagated out to the memory bus where it would need to be if I was relying on a non-volatile memory out there to store my data permanently. And then there's also questions perhaps about integrating, again, that main memory maybe with some sort of internet connectivity so that we can synchronize it with other nodes and optimize the storage system kind of in the large, as I mentioned before, with the data center. There's another set of challenges that face these memories, which have to do with sort of the economics of getting them to be as cheap or hopefully cheaper than something like flash. And that really comes down to finding an application where it's worth the kind of economic expenditure to build large storage systems out of these memories so that we can get to the economy of scale, so that we can start driving down the price of these memories so that they can really compete. And that's going to be I think pretty challenging in the near term, just because flash has such a entrenched position in markets like mobile computing, where it's kind of an ideal technology. It's very dense, it's very cheap, and there's huge volumes. And so it's going to be just from a kind of from the market's perspective, it's a little bit of an uphill battle to get these memories to be widely adopted. But I think if we can solve those first set of challenges in terms of how do we integrate them into systems, and if we can demonstrate that they have real benefit and that we can really leverage them to enable some new applications, that'll help a lot with kind of getting to that economy of scale that'll make them economically feasible.
Thank you very much for joining us today.
Thank you.